I realize this next lesson is just theory, but it's an important lesson that you'll find yourself using constantly whenever programming. In the next lesson, we're going to use the LCD display to actually display information directly from the microcontroller, though it does not have to be the LCD display. Let's say you're building a digital thermostat to control the temperature in a room. Now, besides the LCD giving you a direct display of your settings, etc., it can be invaluable in your research and development phase. Let's say we set up a thermistor with a resistor as a voltage divider across the power supply, and the analog to digital converter spits out a 10-bit number representing the voltage coming out of that voltage divider. Now, I want to turn the heat on when the temperature gets to 20 degrees Celsius, and turn the heat off when the temperature gets to 25 degrees Celsius. Now, I have absolutely no idea what the number the analog to digital converter spits out at 20 degrees. I can't, peer inside of the PIC and put a multimeter on the data lines coming out of the A to D converter. Yet, this is precisely what I want to do. In fact, I need to do, as I need to look inside the PIC somehow to find out what number is being produced when the thermistor is at 20 degrees Celsius. Now, there's a bunch of ways you can do this, some simple, some more complex, but from now on, you'll find yourself running a calibration program or a utility program or subroutine that you specifically wrote just to tell you what the microprocessor sees. The PIC's A to D converter is a 10-bit converter with the lower 8 bits stored in one 8-bit register and the upper 2 bits stored in another 8-bit register. So in our case, we're going to hook up the LCD display and actually display the three nibbles as 3 hexadecimal numbers coming straight out of the A to D converter in real time. We can then measure the actual temperature the thermistor is seeing, copy down whatever number is being produced by the A to D converter, and use those generated numbers to write our final program, which actually controls the heat. So if you can picture it, this is research and development. We're writing a program that will do nothing but spit out numbers for us that we can then use to write our actual final program, which controls the heat in a room. We will know what value is produced by the A to D converter at what temperatures. We'll get a whole range of numbers by experimentation. Now, the thing is, you could build the exact same circuit as I do with the exact same parts, but it wouldn't work the same because of variances in the thermistor and resistor. Now, think about it. So by using this form of direct feedback, you can calibrate your system by seeing a direct feed from the A to D converter. Now, here's another powerful use of the A to D converter you can use in your projects. Let's say you had 10 push buttons for your microcontroller-driven robot. You can set them up as digital inputs on your PIC, but that would use up to 10 digital inputs. You only have so many input-outputs, so you want to conserve them. Enter the A to D converter. By building a resistor ladder like this, it builds a multi-level voltage divider. It will spit out a different voltage for each button you press. Now, you run one line into an analog to digital converter, and that A to D converter will spit out a unique number depending on which button you pressed. So really, you could build a huge array like this, far bigger than you'll ever want. You could easily build an array of hundreds of buttons like this, so you could read hundreds of buttons using only one input on your microcontroller. So now you need to figure out what number gets generated for each individual button. One way you could do this is simply to display the A to D result on the LCD display and simply press each button. Write down what the A to D converter reads when you press a specific button. Use those numbers later on in writing your program. In fact, because pushing 2 buttons at once will make a unique complex voltage divider, a unique number winds up generated by the A to D converter when you press 2 buttons at once. So you can have multifunction buttons. Now, also bear in mind, how you read that information can be done in a number of ways. Your writing a utility program or subroutine in order to do all of this anyway. So pick your method. A single LED on a digital output could be programmed to flash the number so you can simply, count the pulses from the LED. Put a pause between each number. So if it was a hex number, say 25C, you'd see 12 flashes for C, a pause, 5 flashes, a pause, and 2 flashes. This could be done, say, if you didn't have an LCD display handy. Another way of dealing with unseen digital results and numbers is to build a calibration routine into your program. For example, you could have a single LED programmed to flash a certain code and a single button for calibration. You have your manual of instructions that you wrote to go along with your fancy high-tech gadget that you're building. Well, let's say it's our submarine robot, which we're going to design in the next several modules. It's controlled by a joystick. Now here I've opened up this joystick so you can see how it works. It's simply 2 pots on the 2 axes. Stick those pots across the power supply and put the middle pin of each one to 2 analog inputs on your microcontroller. You've now got joystick control. But you have no idea what numbers the analog to digital generates when the joystick is centered, or the full right or left or full up or down. So that's when the user reads your manual of instructions on how to calibrate. When the user presses the calibration button, it flashes the LED 3 times quickly, indicating it's ready to calibrate. The manual of instruction tells the user to now move the joystick as far as it'll go in a big circle. During this time, the microcontroller is looking for the biggest and the smallest numbers generated by the A to D converter on each axis. And it's storing those numbers in memory. After a few cycles, the LED then flashes twice quickly, indicating the user is to let go of the stick so it will center itself. The microcontroller now reads the joystick axes and records in its memory the values it sees when the joystick is centered. These values, now stored in memory, are then referenced from your program so it knows when the user has the joystick centered or is commanding movement in a specific direction. Now, one last note. Because the resolution is pretty high, 1,024 different values, the most minute changes in the input voltage will give a different number. So with any variable resistor, your number will constantly drift a little because of microscopic variations in the voltage. So when you go to use the number coming out of the D to A converter, or the A to D converter in your program, you just need to take that into account. Let's say at 20 degrees C, your thermistor experiments showed that the A to D converter will spit out a number somewhere between 234 and 276. So when you write your program, you're checking to see if the number is greater than 233 and less than 277. You now know that your temperature is at the 20 degree mark.